proposing ideas for technologies that can harness energy sustainably, or pitches, which gave students the opportunity to present their innovative ideas to their peers and a panel of industry experts. Student pitches was such a success last year that this year we added an additive incentive for the students. I am pleased to introduce the winner of this year's Student Pitches event, Shomik Verma. Good luck.
Thanks so much. Thank you. Good morning, everyone. It's great to be here. I'm Shomik. I'm a graduate student at MIT, and today I'll be talking about my work on using thermophotovoltaics coupled with hydrogen combustion for clean and dispatchable power generation. To start off, we all love solar panels because they're clean, they're solid state with no moving parts. However, they're intermittent and only work during the day. In contrast, fossil fuel-based combustion plants are dispatchable. However, they have heavy rotating machinery requiring frequent maintenance, and they emit CO2. So the ideal technology would have the best of both worlds. It would be clean, solid state, and dispatchable. Thermophotovoltaics, or TPV, fits into this category. How TPV works is instead of using the sun as an energy input, we use a terrestrial heat source, such as combustion. Then we can use the same solid state technology as solar photovoltaics, but are now dispatchable. Further, if we get the emitter temperature hot enough, we can use the same band gap materials as solar photovoltaics and take advantage of existing mass manufacturing techniques while generating a substantial amount of power. For the sub-band gap photons shown in yellow, traditionally these would pass through solar photovoltaics, but for thermal photovoltaics, we can reflect them back to the emitter, recycling the photons and improving combustion efficiency. While there's still some loss mechanisms, overall, thermal photovoltaics can get up to twice the efficiency of solar photovoltaics. So this leads us to two questions. First, can we actually make TPV cells that reach these efficiencies? And second, how do we generate the heat source? On the first question, my lab has recently experimentally demonstrated high-efficiency TPV cells at 41%, with a clear pathway to 50% with cell improvements. We also demonstrated extremely high power densities of 10 watts per centimeter squared, which is 500 times greater than that of solar PV, meaning we require 500 times less area to generate the same amount of power. So with these innovations, we've helped solve challenge number one of showing that we can make high-efficiency, high-performing TPV cells. My work has been on solving challenge number two of generating the heat input for TPV. I chose to use hydrogen combustion because it is both clean and dispatchable. In this system, hydrogen is combusted with air, and the heat from combustion is released towards the emitter. The emitter then transfers heat with the TPV cells, as we discussed previously. On the hydrogen side, the post-combustion products are exhaust at high temperatures, so to recover some of that heat, we add a recuperator, which preheats the fuel and air, improving combustion efficiency. Unfortunately, existing combustion TPV devices have low efficiency when compared to turbines and fuel cells. This is due to two main reasons. First is due to poor recuperation, so there's too much heat loss through the exhaust. The other reason is staying at small scales, which means there's high heat loss due to insulation challenges. My design attempts to solve both of these issues using effective recuperation and moving to large scales to push the efficiency higher. Specifically, my design is shown here. In this device, hydrogen and air enter at the bottom, are distributed across several milliscale channels, are combusted at the other end of the device and release heat towards the TPV cells. The high temperature exhaust then flows back and preheats the hydrogen and air. This device features several novel characteristics, including a near isothermal emitter at 2000 Kelvin, a high effectiveness recuperator enabled by the milliscale channels, and ceramics for high temperature stability. When coupled with high efficiency TPV cells at 50%, this enables an overall fuel to electricity conversion efficiency of nearly 47%. Further, the modular nature of this design enables stacking and applications at a wide variety of length scales, especially the large length scales required for easy installation. With these innovations, I've helped solve challenge number two of how to generate the heat source. And fabrication of this design is currently in progress to demonstrate this. Finally, Preliminary techno-economic analysis shows that the hydrogen TPV system is cost competitive in several markets due to the high power density of the design, enabling lower material cost and therefore lower capital cost. I've shown two examples here. First, this has the potential to be a next generation power plant and replace conventional power plants as a cheaper alternative, even when considering NOx control technologies. It's also CO2 free. The second application is for long duration energy storage. In this technology, excess electricity can be used to produce hydrogen, which is the energy storage medium. When electricity is then required, hydrogen can be converted back to electricity on demand. Unfortunately, this last step is currently expensive, but hydrogen TPV is a cheaper alternative to existing fuel cells and can enhance the viability of this long-duration technique. Overall, I first introduced how hydrogen TPV has promising potential, but this has not been practically realized. With innovations in TPV efficiency and a novel combustor design, my lab has contributed to making this technology efficient, dispatchable, cheap, and solid state as an efficient alternative to electricity generation. So if you want to discuss further or want to collaborate with me, please find me afterwards or email me at skverma@mit.edu. Thanks for your time.